Hey everybody, it's Ripley again. We are in chapter 10, man. We're on the home stretch. And these last two chapters are going to be pretty straightforward. There's not going to be a whole lot to them. Chapter 10 in particular is going to be done predominantly on your calculator. There's not going to be a whole lot of lecture to it. I'm just going to show you in class how to plug stuff in. But I do want to give you sort of the foundation for everything, okay? This chapter is about correlation, all right? Correlation is real simple to get your brain around. What it is it's the strength of a linear relationship between two related variables, and these are x, y. Okay? So sometimes you'll hear this term referred to as bivariate data. And let's get you a little bit of background here before we get crazy. Let's say, I mean, there's lots of ways to think about this, but let's just come up with a quick little example to describe it. Let's say that we take I want to know the relationship between SAT English, or SAT Mathematics and SAT, what's the other one? I think it's English score, right? Or verbal score, right? So you got a verbal and you got a math score. So what we do is, let's say we take 20 people, and all that we're going to do is I want to figure out if the verbal score affects the mathematics score. So I don't know what you remember about this from your function, but what you've got is an independent variable and you've got a dependent variable, right? So I mean, really what we're doing here is we're just doing a bunch of x sub n and y sub n's. And in this case, this is going to be our verbal and this is going to be our math. Okay? So I would just go up to 20 people and I'd say, hey, what'd you get on your verbal? And they'd be like, oh, I got a 650. Okay, what'd you get on your math? Oh, I got a 720. And that would be our first, this guy right here would be, think of this almost as our first data value. And then I'd go up to somebody else, what'd you get on your verbal? Oh, I got a 420. What'd you get on your math? I aced that. I'm awesome at math. Okay, you see what we're doing? So, and I would end up with 20 values, because n is the number of ordered pairs. Now, don't think of ordered pairs so much like you do with when you're talking about geometry or you're talking about functional theory. All right, what we're doing is we're talking about a relationship between an independent and a dependent variable. And then what we do is, just like always, we graph them. Now, think about this. You could have, if I plot all of these points on a graph, and I end up with something. Let's say that they're 20 like this. I got a couple crazy ones. And I end up with that. Now, does there appear to be a strong linear relationship between, so these, what did I say? These are my verbal scores, and these are my math scores. Well, now, there's certainly not as strong a linear relationship as if I did this and this, right? This would be a perfect linear relationship, right? Or something like this. If I had a point here and a point here, whoops, and a point here and a point here, I think that's perfectly linear, yeah, then that would have a perfect linear relationship. But this guy right here is just approximately linear. All right, there certainly appears to be a linear relationship between the x and the y variables. All right, but what we need is something that measures the strength of that linear relationship. How about this? What if I did something like this? Let's go back to black. Let's say that I had a bunch of points that looked like this. Well, think about it. If I tried to draw a line through this that was supposed to be representative of the data, would it be that one? Would it be that one? Would it be that one? Or that one, you know what I'm saying? This one's pretty easy to tell. I could actually just kind of draw a line. You know, that's supposed to be, we could call that, I suppose, a trend line. We'll get more technical with what we call it here in just a little bit. All right? So this has a relatively strong linear relationship. This, on the other hand, has nothing. Now, couldn't we also have data that did something like this? You see that? Now, your spidey sense may be tingling. And you maybe say, well, okay, it doesn't have a linear relationship because I would either want to draw a line this way or I'd want to draw a line this way. And if I wanted to trend through all of the data, I'd probably end up with a line that looked like this. And that line is not representative of any of the data. So this has what's called a curvilinear relationship. Curvilinear relationship. Now, correlation, for what we're talking about, correlation has nothing to do with curvilinear. All right, I think there's two L's in curvilinear, by the way. We are only measuring the strength of the linear relationship between the two data, between the independent and the dependent variable. All right, now there's a way to measure that. Of course there is, otherwise we wouldn't be talking about it, right? And that's called Pearson's coefficient. So the Pearson's correlation coefficient. And we're going to keep this simple. If you look in chapter 10.2 and you look at the formula to come up with Pearson's correlation coefficient, which is known as R, the formula is god-awful. It's horrendous, and it's completely unnecessary for what we're doing. To be honest with you, I think I've had to do Pearson's correlation coefficient one time by hand, and I wanted to poke my eyes out for having done it. Excuse me, I gotta get a drink. All right, but Pearson's correlation coefficient it's the measure of linear, it's the measure of the strength of the linear, just linear for now, okay? You'll get into more heavy topics down the road in your future statistics courses, but for now, just think of it as the linear relationship between variables, between independent, which is the x, and dependent. Sometimes you'll hear these referred to as predictor variables, dependent, which is the y variables. Okay? Now, like I said, everything that we do in here is going to be done on the calculator, and we're going to do it in class. So don't freak out, okay? I promise we're not going to have to do any of these by hand because they're absolutely horrific. All right, you ready? R always lives between -1 and 1. Always. Now, let me give you an example. Back here, the strength of the linear coefficient for this set of values would be approximately 0 because there wasn't anything. In this case, R would be a perfect 1. In other words, there is a line that passes through all of the points. Now, there's a bit of confusion here that you have to try to avoid. Notice maybe a little bit, I don't know, I didn't mean to obfuscate anything here, but this may be a little confusing because the slope of this line is also 1, all right? But R doesn't have anything to do with the slope except that they always share the same sign. I'll show you. For this guy, R equals -1. It's a perfect linear relationship. However, it's going in the negative direction. Do you remember, you've probably seen this before, where you talk about negative relationships versus positive relationships. Excuse me. In statistics, that's really what we're measuring here. All right. Now, this guy over here, I don't know if I had to guess, and we're not actually going to go through it. Like I said, we're going to do all of this in class with our calculators because it's so much easier. I would guess that the strength of the linear relationship on this would be probably about maybe positive 0.9. All right. So let's go back over here, and we are definitely going to say that this is not a slope. Okay? All right. Now, I'm going to show you how to test. It's so simple. You guys will giggle. You simply use a test at the back of the book, out of the appendix, to prove whether or not there is a linear relationship, whether or not we can actually claim that there's a linear relationship between variables. Okay. However, we're going to have to talk about some assumptions. Okay, let's play around with some terminology first and foremost. Okay, correlation, because I don't want to get too far ahead of myself. You may have heard this before. Correlation does not imply causation. All right? In other words, if two variables are very highly correlated together, there's no guarantee that one causes the other. In other words, let's say that I'm going to let my independent variable be number of pickles. I've eaten in lifetime. Okay? And this is going to be a number of classes. It's two S's. I've taken in lifetime. Well, you could probably, I mean, depending on your pickle eating habits, and if I went and I just went to a bunch of people, and let's assume that we can gather the data, right? If I go to certain number of, it really doesn't matter the age of the people. I mean, the older I am, the more pickles I've eaten, and the older I am, the more classes I've taken, right? I mean, even somebody who dropped out of school, I might end up with a relationship that looks like this. I know this is a silly problem, but just bear with me, okay? So let's say that N equals, I go out and I gather 30 pieces of data. In other words, I ask 30 people, how many pickles have you eaten in your lifetime? And they're able to remember, let's say that. And how many classes have you taken in your lifetime? And they say, I don't know, 75 or whatever. And let's say that our R, we end up with this fantastic correlation coefficient, which is, let's say, 0.95. Now, careful here. Again, remember, the correlation coefficient is not the slope of the line. Clearly, that slope, the slope of this line is not about 0.95. It could be really, really steep positively and still only have an R of 0.95. The biggest that the correlation coefficient can be is 1, and the most negative it can be is -1. All right? Now, this right here is a very strong correlation coefficient. It's very strong. However, we can't say that the number of pickles that you eat causes you to take classes, or vice versa. I can't use the inverse property and say, well, the number of classes that I take causes me to eat pickles. So correlation does not imply causation. All right. Now let's talk about our assumptions. All right, assumptions to be able to play. Really, the only assumption to be able to do a correlation coefficient is we just need an SRS, all right? That's all that we really need. We just want to make sure that we gather our data from a simple random sample. Now, here's the problem, is I don't know, like this one seems to have a real strong linear relationship between the variables, badly drawn, right? But what if I have this guy? What if I have, say, I don't know, a whole bunch in here, and then all of a sudden I got a couple down here, and a couple up here, and a few there, okay? Now, can I look at that and say, okay, that's a linear relationship. It appears to be trending here, but really is it? I mean, is it easier to draw a trend line this way, okay? Now, like I said, your calculator is going to compute your correlation coefficient. So what you're going to do is just like, I mean, think about it as a coordinate tree. All you're going to do is you're going to have a whole bunch of points, x's and y's, that you're going to put in your calculator. And then your calculator is going to spit out R. It's also going to spit out a bunch of other stuff. It's going to spit out an R squared, et cetera, okay? Now, let me just give you the terminology here, because there's really not a whole lot to this. The null hypothesis for testing whether there is a linear relationship between variables is this. This is a row, it's not a P. So it's a badly drawn lowercase Greek row. All right? We're testing whether or not row, now can you see why it's a row? Remember, lowercase Greek letters are considered the parameter. So the true parameter, the true population correlation, is going to equal 0. Now, I'm going to write over here in red. This implies no linear relationship. Okay, versus my alternative hypothesis, which is rho is simply not equal to 0. Now, the book gives you a whole bunch of ways to do this. We're going to keep it absolutely simple. Just use test, statistic, R, and table, what is A5? Use test statistic R and table A5. And I will go over, just take a peek at table A5. It's in the little blue area of the appendices of your textbook. And if you look at them, and I'm not going to clearly, I mean, if you crack open your book with me right now, it's so easy to use the table, and it's fantastic because all it's got is, it's got N, and then it's got a bunch of numbers. So it starts at 4, and then 5, and then 6, and it comes down here to 100. And then it's got alpha equals 0.05 and alpha equals 0.01. Those seem to be the biggies, right? And then all it does is it gives you values that R has to be bigger than. So for 4, it's got a 0.95. For 0.01, it's got a 0.99. So if all I have are 4 data values, if all I have are 4x1, y1, x2, y2, x3, y3, and x4, y4, and I'm trying to claim a linear combination, a linear relationship between these, then when everything is said and done, R, if I want to test this at alpha equals 0.05, then R had better be greater than 0.95. Okay, now for 6, let's see, if I look in here, so if I've got 6 values, watch how quickly it goes down. At alpha equals 0.05, I've got 0.811 and 0.917. So if I'm testing this thing at alpha equals 0.01, then R had better be greater than 0.917. If they are, now think about that. If R is greater than 0.917, I reject the null hypothesis, and we have a linear relationship. That's it. That's all that there is to it. Now, all of this is going to be done on your calculators. So I don't want to waste a bunch of time, and you guys would go nuts. You'd probably throw your computers out the window going through the hand calculations. Because if you look on page 498, the hand calculations are absolutely horrific. So we will go through this together in class. All right? Believe it or not, guys, that's it. All right, we'll see you in class tomorrow. We'll do some correlation coefficient. I'll see you in the next